Good morning, dear students. Welcome back to physics class. Today, I would like to discuss on the topic Dimensions of Physical Quantities Part B. The subtopics are A. Limitations of dimensional analysis, and B is related numerical. In last class, you had studied about dimensional analysis and its applications. For today's class, at first, I would like to say about the limitations of dimensional analysis. What are the important limitations of dimensional analysis? Let me see that. First one is the method of dimensions can only test the dimensional validity but not the exact relationship between physical quantities in any equation. It does not distinguish between the physical quantities having same dimensions. That is, it is not a solution. It can check only if the equation is dimensionally correct or not, but we cannot say the equation is absolutely correct. Second one is, it cannot derive relation or formula if a physical quantity depends upon more than 3 factors even though they are having same dimensions. It means that it cannot be applied to an equation involving more than 3 physical quantities. Third one is, dimensionless constants cannot be obtained by this method. That is, it cannot determine the value of dimensionless constants, which can be determined by the experimental methods or other scientific methods. Fourth one is, it does not test whether a physical quantity is a scalar or a vector quantity. And fifth one is, it cannot derive a formula containing trigonometrical function, exponential function, and logarithmic function. That is, we cannot use this method to equations involving trigonometric function, exponential function, and logarithmic function. On next, let's be discuss on some numerical. Question number 1. Check the correctness of physical equation. S is equal to ut plus half at square. In the equation, S is the displacement, u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time in which change occurs. What is its solution? Given that LHS equal to S and RHS equal to UT plus half AT square. In the form of dimension, the LHS of the given equation S can be written as dimension of S is equal to dimension of L the power of 1, M the power of 0, T the power of 0. It is the equation number 1. We know that RHS is UT plus half AT square. Similarly, the dimensional formula for the RHS can be written as dimension of RHS is equal to dimension of L the power of 1, M the power of 0, T the power of minus 1 into dimension of L the power of 0, M the power of 0, T the power of minus 1 plus dimension of L the power of 1, M the power of 0, T the power of minus 2 into dimension of L the power of 0, M the power of 0, T the power of 0 is equal to dimension of L the power of 1, M the power of 0, T the power of 0. This is the equation number 2. Note that the constant 1 by 2 is dimensionless, which is ignored. From the expressions 1 and 2, we have dimension of LHS is equal to dimension of RHS. Hence, by the principle of homogeneity, the given equation is dimensionally correct. Question number 2 is, let us consider an equation 1 by 2 mv square is equal to mgh, where m is the mass of the body, v is its velocity, g is the acceleration due to gravity, and h is the height. Check whether this equation is dimensionally correct. Solution is, given that LHS as 1 by 2 mv square and RHS as mgh, the dimensions of LHS is dimension of LHS equal to dimension of m into dimension of L t the power of minus 1 the whole raised to 2 is equal to dimension of m into dimension of L the power of 2 t the power of minus 2 is equal to dimension of m L the power of 2 t the power of minus 2. This is the equation number 1. So, the dimensions of RHS is dimension of RHS is equal to dimension of m into dimension of L t the power of minus 2 into dimension of L is equal to dimension of m into dimension of L the power of 2 t the power of minus 2 is equal to dimension of m L the power of 2 t the power of minus 2. This is the equation number 2. From the expressions 1 and 2, it is seen that the dimensions of LHS and RHS are the same. Hence, the equation is dimensionally correct. Third question is, check the correctness of the physical equation v square is equal to u square plus 2a square using dimensional analysis. What should be its solution? Given that in the form of dimension, the LHS of the given equation v square can be written as dimension of v square is equal to dimension of L the power of 1, m the power of 0, t the power of minus 1 the whole raised to 2 is equal to dimension of L the power of 1, m the power of 0, t the power of minus 2. This is the equation number 1. We know that RHS is u square plus 2a square. So, the dimensional formula for the RHS can be written as dimension of RHS is equal to dimension of u square plus 2 into dimension of a into dimension of s square. Then dimension of RHS is equal to dimension of L the power of 1, m the power of 0, t the power of minus 1 whole raised to 2 plus dimension of L the power of 1, m the power of 0, t the power of minus 2 into dimension of L the power of 1, m the power of 0, t the power of 0 whole raised to 2 is equal to dimension of L the power of 2, m the power of 0, t the power of minus 2 plus dimension of L the power of 1, m the power of 0, t the power of minus 2 into dimension of L the power of 2, m the power of 0, t the power of 0. So, dimension of RHS is equal to dimension of L the power of 2, m the power of 0, t the power of minus 2 plus dimension of L the power of 3, m the power of 0, t the power of minus 2. This is the equation number 2. Here you have seen that we have multiplied the dimension of the same base quantities. So we have got the RHS in the form of these expressions. From the expressions 1 and 2, we have seen that dimension of LHS is not equal to dimension of RHS. So, by the principle of homogeneity, the equation is not dimensionally correct. Fourth question is, a famous relation in physics relates moving mass m to the rest mass m0 of a particle in terms of its speed v and the speed of light c. This relation first arose as a consequence of special theory of relativity due to Albert Einstein. A boy recalls the relation almost correctly, but he forgets where to put the constant c. He writes m is equal to m0 divided by 1 minus v square the whole raised to 1 by 2. Guess where to put the missing c. What should be its solution? First we have to write the given expression from the question. M is equal to m0 divided by 1 minus v square the whole raised to 1 by 2. And also we have to write the dimensions of m, m0, v, v square and c from the expression. You know that the given formula will be dimensionally correct only when the dimensions of LHS is same as that of RHS. You have to check both sides of the expression again. You can understand that this is only possible when the factor 1 minus v square the whole raised to 1 by 2 is dimensionless. How to make this form to be the dimensionless? We have to divide v square by c square. Then the denominator becomes dimensionless, so it can be ignored. Hence, the correct relation is m0 divided by square root of 1 minus v square by c square. Here the square root is only for 1 minus v square by c square. Fifth question is, the centripetal force F acting on a particle which is moving uniformly in a circle depends on the mass m of the particle, its velocity v and radius r of the circle. Derive dimensionally formula for force F. Solution is, given that the centripetal force F acting on the particle depends on the mass m of the particle, its velocity v and its radius r. So, it can be written as F is directly proportional to m the power of a into v the power of b into r the power of c. Therefore, F is equal to a constant k into m the power of a into v the power of b into r the power of c, which is the equation number 1a. Where k is a constant, it is dimensionless. Putting the dimensions of each quantity in the equation, so we will get the dimension for F is dimension of m the power of 1, L the power of 1, T the power of minus 2 is equal to dimension of RHS equal to dimension of m the power of 1, L the power of 0, T the power of 0 whole raised to a into dimension of m the power of 0, l the power of 1, t the power of minus 1 whole raised to b into dimension of m the power of 0, l the power of 1, t the power of 0 whole raised to c is equal to dimension of m the power of a, l the power of b plus c, t the power of minus b. Here we have to equate the exponents or powers from the dimensional forms of the base quantities m, l and t on both sides of the expressions. Then we get a is equal to 1, b plus c is equal to 1 and minus b is equal to minus 2. So we get a is equal to 1, b is equal to 2 and c is equal to minus 1 from 2 and 3. Substituting the values of a, b and c in the expression 1a, we get f is equal to k into m the power of 1, v the power of 2, r the power of minus 1, which is equal to k into m v square by r is equal to k m v square by r. This is the formula for f which is dimensionally obtained. Sixth question is, the kinetic energy k of a rotating body depends on its moment of inertia I and its angular speed omega. Consider the relation to be k is equal to k into L the power of a omega the power of b, where k is dimensionless constant. Find a and b moment of inertia of a sphere about its diameter is 2 by 5 m r squared. The solution is, given that the kinetic energy k of a rotating body depends on its moment of inertia I and its angular speed omega. Now we have to write the dimensions of kinetic energy k, moment of inertia I and angular speed omega. By applying the principle of homogeneity in dimensions in the equation k is equal to k L the power of a omega the power of b, we get the dimension of LHS is dimension of m the power of 1, L the power of 2, t the power of minus 2 is equal to dimension of RHS, which is dimension of m, L the power of 2, t the power of 0 whole raised to a into dimension of m the power of 0, L the power of 0, t the power of minus 1 whole raised to b. As k is a dimensionless constant, so it has ignored in the dimensional form. So we will get in the form of dimension as the dimension of m the power of 1, L the power of 2, t the power of minus 2 is equal to dimension of m the power of a, L the power of 2a, t the power of minus b. By equating the exponents or powers from the dimensional forms of the base quantities on both the sides of the expression, we will get a is equal to 1 and b is equal to 2. So k is equal to I omega square. By considering the dimensionless constant k, the expression takes in the form of capital letter K is equal to k I omega square. Seventh question is, Hooke's law states that the force F in a spring extended by a length x is given by F is equal to minus kx. According to Newton's second law of motion, F is equal to ma, where m is the mass and a is the acceleration. Calculate the dimension of the spring constant k. Solution is given that the expression F is equal to minus kx. Then k is equal to minus F by x, as F is equal to ma by Newton's second law of motion. The dimensions of force can be written as dimension of F is equal to dimension of ma is equal to dimension of m the power of 1, l the power of 0, t the power of 0 into dimension of m the power of 0, l the power of 1, t the power of minus 2 is equal to dimension of m the power of 1, l the power of 1, t the power of minus 2. Similarly, the dimensions of spring constant k also can be written as dimension of k is equal to dimension of F divided by dimension of x. We know that dimension of x is equal to dimension of m the power of 0, the dimension of l the power of 1, t the power of 0. So, the dimension of k is equal to dimension of m the power of 1, l the power of 0, t the power of minus 2, or dimension of m t the power of minus 2. And eighth question is, compute the dimensional formula of electrical resistance R. What should be its solution? The solution is V is equal to IR by Ohm's law. R is equal to V by I. Since work done W is equal to Q into V, where Q is the charge and V is the electrical potential difference. So, R is equal to W divided by Qi is equal to W by I square T. We know that current I is the time rate of flow of charge. So, it will be equal to Q by T. First, we have to write the dimension of work W, which is equal to dimension of m the power of 1, l the power of 2, t the power of minus 2. Similarly, we have to write the dimension of R is equal to the dimension of W divided by dimension of Qi, or the dimension of W divided by the dimension of I square T, which is equal to dimension of m the power of 1, l the power of 2, t the power of minus 3, a the power of minus 2, since dimension of current I is equal to dimension of A. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.